Hey everybody, this video is the first video in a series of videos that I'm going to do that pertain to something called the gas laws. The gas laws describe the behavior of gases. It's similar to traffic laws and how those dictate how we drive on the road. The gas laws dictate how gases behave in everyday life. Now, we already talked about what gases are like in a previous video lesson on the states of matter, but these next four statements describe how gases behave specifically. Keep these four things in mind and apply them to any time we are talking about a sample of any gas. The first thing that we need to say is that the particles of the gas are very small. They're so small, in fact, that you can't see them with your eye, but they exist because we know that the particles are there. When the wind blows against our body, we know because it pushes back on us. If we are walking into the wind blows hard and pushes us backwards. That means gas is made of particles, and those particles are very small. The next thing we know about gases is that the particles never stop moving. Even if you're in a classroom or in your living room and it doesn't feel like the gas particles are moving, they're always moving. They may not be moving as fast as when the wind is blowing very strongly, but trust me, the particles are moving. If you could see on a microscopic level, which you can't, you would be able to see the gas particles, and they're moving all around you all the time. The next thing is that particles of gas can collide with one another, and they can also collide with the container that they're being held in. But when they do collide, they don't slow down. They bounce off each other and the walls without slowing down. The last thing that we need to know about gases is that the particles do not attract one another. Some particles do attract each other, but we're going to assume that the particles of gas don't attract, and if they don't attract, they don't slow down. When two particles do attract one another, they slow down their movements as they pass by, because it's like two magnets, and they feel a connection to the other particle, and they lose some speed. But we're going to assume that the particles don't attract each other, and thus they don't slow down. These four statements are the beginning of the conversation about the gas laws. Now, last chapter we talked about physical properties and chemical properties. This particular slide, we're going to talk about the physical properties that pertain especially to gases. If I ask you to describe a gas, there are four different measurements or four different properties of a gas that you would probably talk about. The first one is temperature. The second one is pressure. The third is volume. And the fourth is quantity of particles. These four measurements of gases are very important, and they're very interconnected with one another. If you change the temperature of a gas, the pressure, volume, and number of particles may change. And so we're going to talk about the connectedness between these four gas properties. We call them the gas variables, and we will discuss each one individually now. The first gas variable is called temperature. And temperature is basically how fast the particles of gas are moving. When you add heat to a substance, you are making the particles move faster. If the particles move faster, the temperature increases. On the contrast, if you cool off a substance, meaning you take its heat away, the particles slow down and the temperature decreases. There are three basic ways that scientists measure temperature. The three different scales are Fahrenheit, Celsius, and Kelvin. Degrees Fahrenheit is the temperature unit that we use here in the United States, but of the three, it is the least useful for scientists to use. Now, degrees Celsius is a temperature unit that is very useful, especially when you're discussing water. Water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. It's easy for people to remember 0 and 100. Which is why it's useful when describing water. But Kelvin, the last one, is probably the one you know the least amount about, but it is the most useful when discussing the temperature of gas particles. Let's talk about the comparison between degrees Celsius and Kelvin. And main difference is that degrees Celsius begins at negative 273 degrees Celsius. That's the coldest that cold can possibly get. But Kelvin starts at 0. And because of that, you can never have a negative value on the Kelvin temperature scale. Now, 1 degree Celsius is equal to 1 Kelvin. You go up from 1 degree Celsius to 2 degrees Celsius. That's the same as going from 1 Kelvin to 2 Kelvin. But the starting temperatures are different. Starting at the coldest of cold, temperatures in degrees Celsius is negative 273. But for Kelvin, they are 0. And only positive numbers then can apply in the Kelvin scale, which makes it useful for doing math when you are doing math with gas laws. So let's scroll down here a little bit and give us some more room. As I mentioned, 1 degree Celsius is the same as 1 Kelvin. So the temperature degree and Kelvin are equivalent to one another. You go up 1 degree Celsius, you go up 1 Kelvin. Now because the degree Celsius scale starts at negative 273, then if you ever want to figure out what Kelvin is in temperature, you just take the degree Celsius and add 273 degrees to it, and you get yourself the Kelvin temperature. Now, I will probably only give you the Kelvin temperature in any math problem that we're going to do because I don't want to screw you up. But I just want you to know that the easy conversion is take the degrees Celsius and add 273. For example, if room temperature is 25 degrees Celsius, then add 273 to that, and you get 298 Kelvin. And so 25 is equal to 298, but they're different temperature scales. The next gas variable that we're going to talk about is called pressure. And pressure is how much force a gas is pushing inside the container that is holding the gas. Like a balloon, for example. When you put gas inside a balloon, the gas fills the balloon and it exerts a force or a pressure on the inner wall of the balloon. And that force applied to the inner wall is called pressure. The force comes from the particles as they bounce around and strike the wall. All these particles are always in constant motion and moving, and as they push or hit the wall and bounce off in another direction, they keep the balloon inflated. Without the pressure of the gas inside the balloon would not blow up. Now, if you are good with cars or bikes, maybe you know that the pressure inside a tire is usually measured in PSI, or pounds per square inch. But once again, that's not useful for us as scientists. So instead, we use a different pressure unit known as atmospheres, or ATM for short. So the atmosphere is a unit of pressure that we use. If you ever look on the side of a tire, maybe it be a car tire or a bike tire, you might see the measurement, the suggested pressure reading in pounds per square inch, but sometimes you see it listed in atmospheres. And so now you know what that means. It's a pressure unit of gas inside a tire. You might be wondering, how are pounds per square inch and atmospheres related? I tell you that usually a tire is suggested that you fill it up to 30 psi, or 30 pounds per square inch. Well, that's roughly equal to about 2 atmospheres of pressure. Now, you'll never have to know that. I was just kind of telling you for context. The third gas variable is volume, and volume is defined as essentially how much space a gas takes up. If a particular sample of a gas takes up a large area, then we say that it has high volume. And if it takes up a small area, then we say it has low volume. Volume is measured in liters. Now, liter is a unit that you might be familiar with because a lot of times liquid volume is measured in liters. You can buy soda or water in 1 liter increments. But liters is not actually a quantity. It is actually the amount of space that water bottle is taking up. So if you put a water bottle on your desk and it says it's 1 liter, what it's really saying is how much space it's occupying on your desk. The last gas variable that we'll talk about, the fourth and final, is called number of particles. And just like the name suggests, we're just simply counting how many particles of gas are in a sample of gas. So if I say you have 12 particles, well then you have 12 particles. There's nothing really to say about it. There's no fancy unit for number of particles. If I say you have 1,000 particles of gas in a container, then you have 1,000 particles of gas. So we're just simply counting molecules of gas. Typically in any of our experiments that we do, we are going to keep the number of particles constant, and that will never change throughout the duration of the experiment. Or if I'm discussing a particular gas law, or in a next video lesson, you will be given a specific amount of particles, and you won't really need to worry about it. After you know how many there are, just forget about it. It's useless information, because the number of particles is going to remain the same throughout the entire problem. Well, that takes care of this video lesson about the gas law variables. Thanks for watching.